Hello there and welcome back to the Science Sleepy Minds, where tonight we're getting intimate with something so weird, so quietly terrifying, and so hilariously misunderstood that it might just bend your brain in half before bedtime. You're curled up here for a deep dive into the mystery of time dilation, Einstein's bizarre little trick that makes time stretch, shrink, and totally ignore what your wristwatch thinks it's doing. Right now, imagine you're sitting on a quiet train platform at dusk. A slow breeze nudges the tips of tall grass beyond the rails. The station clock ticks with such steady indifference you'd think it's never heard of quantum mechanics. And then, right on cue, a silver passenger train glides past, slicing the quiet with a gentle hum. Now here's the thing, if you had Einstein's brain, this totally ordinary moment would light up like a scientific fireworks show. Because time, yes, actual time, is moving differently for the people on that train than it is for you. No, not in a metaphorical way. In a very real, measurable, your hair would be slightly shorter if you were on board kind of way. You probably won't survive this train of thought. But let's go anyway. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And tell me in the comments where you're tuning in from and what time it is in your part of the universe. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're still on that platform, still staring down the track, but now the scene changes. It's no longer dusk in your quiet corner of the world. It's 1905 in Bern, Switzerland. A young patent clerk named Albert Einstein is late for work again, probably mumbling to himself about clocks and light rays and the unbearable linearity of his day job. He's the very picture of chaos. Hair like he combed it with a balloon, coat too big for someone who thinks about the fabric of space-time, and eyes constantly scanning reality for cracks. On his way to work, legend says, he stares out the window of a moving tram and wonders, what would happen if he chased a beam of light? And not in a poetic, sunset-chasing way. Number. Literally. What if you moved at the speed of light? What would the light look like? Would it freeze? Would the world freeze? Would time itself hold its breath? From this thought, spiral came one of the most iconic revolutions in science, special relativity. At its heart is the wild notion that time, your constant companion, your alarm clock tyrant, your birthday enabler, is not actually constant. It bends, it stretches, it misbehaves, and it all begins with one ridiculous, stubborn truth. The speed of light is always the same for everyone. Light doesn't care how fast you're moving. You could be standing still or racing on a spaceship, or backflipping on a rocket-powered trampoline. If you measure the speed of light, you'll always get the same result. 299,792,458 meters per second. Exactly. This drove physicists absolutely bonkers, because if light speed can't budge, something else must give way to make the math work out. And that something turned out to be time, as in your seconds, your minutes, your heartbeat. All up for negotiation, depending on how fast you're moving. Einstein realized that two people moving relative to each other will experience time differently, not as a metaphor, literally. A clock moving at high speed ticks more slowly than a clock at rest. It sounds like a riddle, but it's real. Here's the historical hook for you. The idea that time was absolute, that it ticked the same for everyone, everywhere, had been physics gospel since Sir Isaac Newton scribbled in his notebooks back in the 1600s. Newton believed in absolute time, flowing steadily like a universal river. Einstein cannonballed into that river and made it swirl. Quirky tidbit for your pillow. Einstein had no access to modern labs, particle accelerators, or time-slowing watches. He was working entirely with thought experiments, Gedanken experiments as the Germans say, just brain puzzles and logic. That train window we mentioned, it may be the most productive daydream in scientific history. Historians still argue whether Einstein was the first to notice these consequences of moving clocks. Other physicists like Lorentz and Poincaré had scratched at the surface, but Einstein stitched it into a coherent theory with one bold assumption. No frame of reference is special. If you're in a moving train or sitting on a bench, physics doesn't care. The laws stay the same, and so time must flex to keep light constant. So back to the train. Imagine a beam of light bouncing between two mirrors on the floor and ceiling of the dining car, like a fancy metronome. If you're on the train, It seems to bounce straight up and down. But to someone outside watching the train zoom past, the light beam takes a longer diagonal path, like a tiny glowing zigzag. It has to cover more distance to keep up, but light can't speed up to compensate. Remember, it's stubborn, so the only solution is for time to slow down on board the train. Boom, time dilation. It's not magic, it's math. Now, no need to panic. If your cousin takes a quick ride on a high-speed train, they won't come back noticeably younger. Time dilation only gets dramatic when speeds approach light, but even small effects can be measured with atomic clocks. And yes, we've done that. But that's for another night. You ease back on your pillow now, letting the thought settle. What if time isn't a universal truth, but a local rumour, a kind of custom-tailored experience, always a little warped by your motion through the cosmos? Don't worry, there's no quiz. Just remember that for Einstein, the ticking of a clock depended on who was watching, a revolutionary idea that shook physics to its dusty core. And to think, it all started with a man on a tram chasing a beam of light, probably wishing someone else would patent that stupid electric toothbrush. You sit with that dizzying thought. Time, which you've always trusted like a loyal dog, is suddenly acting more like a cat, aloof, conditional, and deeply uninterested in being consistent. But before you start doubting your calendar or wondering if your next birthday might arrive late due to personal velocity, let's stretch this strange new muscle of understanding just a bit further. You're still on the platform. That train, it's long gone. But now you're holding two clocks, one in each hand. Identical atomic clocks, precise down to the nanosecond. And because you're just that curious, you decide to keep one on the platform and strap the other one onto the next train that pulls in. You hand it off to a very patient conductor and ask him to zip around the countryside for a while, just for the sake of physics. When the train returns and you reunite the clocks, something quietly absurd happens. They no longer agree. The clock that stayed with you ticks along, smug and unchanged. The one that took the ride, it's lagging behind, not broken, not defective, just slower, as if the time it experienced was less than the time you did. And the kicker, this isn't theory anymore, it's been tested. That's the heartbeat of time dilation. Motion changes the pace of time. The faster you go, the slower your clock ticks, relative to someone at rest. But don't go imagining people walking around with visibly stretched minutes. It's only noticeable when your speed starts flirting with the speed of light. At pedestrian speeds, your seconds still behave. Mostly. Now here's where it gets even more maddeningly beautiful. It's not just speed that plays with your ticking clocks. Gravity gets a say too. If you climb to a high altitude, say the top of a mountain, or if you're feeling ambitious, orbit aboard the International Space Station, you're technically experiencing time a smidge faster than people below. Why? Because gravity also warps time. The stronger the gravity, the slower time moves for you. So, yes, people living at sea level age slightly more slowly than those in the mountains. Not enough to brag about, not enough to skip sunscreen, but enough that GPS satellites which orbit high above Earth have to correct for it. Otherwise their clocks would slowly drift out of sync with ours down here, and your map app would drop you off in someone else's driveway. Let's take a historical breather here, because this kind of thing used to drive folks absolutely batty. Back before Einstein broke the universe in the most elegant way imaginable, people assumed time was like a big invisible metronome in the sky, clicking away at the same rhythm for all things, always. Newton, that apple-fearing genius, said time flows equably. Basically, time marches on with or without you, and it's not taking shortcuts. But Einstein, he gave time a driver's license and a gravitational diet plan. He said, nope, time's got flexibility. It stretches, compresses, and is 100% not what you thought it was. And here's your quirky fringe tidbit to toss into the sleep pile. During an experiment in 1971, scientists flew 4 atomic clocks aboard commercial airliners travelling eastward and westward around the world. When the clocks were compared to reference clocks left on Earth, the moving ones had shifted, just a tiny bit, but enough to prove Einstein right. They called it the Hayfel-Keating experiment, and it remains one of the most charming examples of science booking a round-trip flight just to mess with time. Historians still argue whether these early experiments were decisive or just cleverly suggestive. After all, measuring billionths of a second in the 1970s wasn't exactly a walk in the lab. but even skeptics had to admit something strange was definitely going on. So you sit there, one clock ticking quietly in your palm, the other returning from its joyride ever so slightly behind schedule. You haven't broken time, but you've started to notice its seams, its give, its tendency to be less of a law and more of a local guideline, and this realization, it gets weirder the more you think about it. Imagine two people walking side by side down the street. Same direction, same pace. Their clocks tick in near-perfect harmony, but now give one of them a jetpack. As they zoom off, their time starts drifting, imperceptibly at first, but real. Their wristwatch is no longer a loyal mirror to their twin on the sidewalk. Now, apply this idea to astronauts. When they orbit the Earth at thousands of miles per hour, their clocks really do tick slower than ours. Tiny amounts, but measurable. An astronaut aboard the ISS for 6 months returns to Earth having aged less than someone who stayed behind. By just a few milliseconds. But still, technically younger. NASA's cheapest anti-aging plan. And yet, time isn't broken. This isn't paradox. It's the universe following its own strange rules, which Einstein was just thoughtful and annoying enough to point out. You're probably wondering now, if everyone has their own version of time, how can anything be objective? How can we trust time at all? The answer, you don't. But you can synchronize. Science handles the chaos with relentless precision. Atomic clocks are corrected constantly for gravitational and velocity-induced shifts. GPS satellites run different algorithms depending on their orbital altitude and speed. Engineers have built an entire system that keeps Earthlings on the same page, despite the fact that our pages are moving, stretching, and occasionally disagreeing. You take a deep breath. The clock in your mind ticks softly, and for a moment you feel untethered, like you're floating in a bubble of time that's yours alone. And maybe you are. After all, as Einstein once said, the distinction between past, present, and future is only a stubbornly persistent illusion. But illusions, as you know, can still make you miss your train. Let's follow a beam of light now. Just one little photon, zipping across space at the universal speed limit. It doesn't matter if it's bouncing off a mirror, beaming from a headlight, or escaping a star on the other side of the universe, it always travels at exactly the same speed. No speed boosts, no sluggish detours. Light is the diva of the cosmos. It never changes for anyone. This idea might seem simple. It is absolutely not simple. Because the moment you accept that light speed stays constant, even when the source is moving, you end up having to accept that time itself must flex to keep the math balanced. And that's where things start to unravel in the most deliciously weird way. So imagine you're floating in space, in a nice quiet ship. No sound, no gravity, just your heartbeat, and the gentle hum of the life support system. Across from you is a light clock. Think of it like this. Two mirrors facing each other, with a photon bouncing up and down between them like a cosmic ping-pong ball. In your ship, you see that beam bouncing perfectly vertically. Ping-pong, ping-pong. It takes a certain amount of time to complete each round trip. That's your standard tick. Now, someone else is watching you. Maybe they're floating outside the ship, or maybe they're watching from a nearby moon. But from their perspective, your ship is moving. And because your whole light clock is travelling sideways, that little photon now appears to be tracing a diagonal path. Up and forward, down and forward. Like it's zigzagging rather than bouncing straight. Here's the kicker. The diagonal path is longer, but light speed must stay the same. So if the light has farther to travel but can't go any faster, the only thing that can change is time. The tick must take longer. That means time is moving slower on your ship than for the observer watching from outside. Boom. That's time dilation, courtesy of a humble photon and two mirrors in space. And it's not just theoretical. This exact thought experiment became one of the key tools for helping physicists, and poor, exhausted physics students, understand why time dilation isn't just a quirky feature, it's baked into the universe. Einstein's light clock was never built in real life. Too many mirrors, not enough chill, but it holds up under the toughest scrutiny. Because it shows, so clearly, that the rules of time are tied to the rules of light. Mainstream historical sidebar for your sleepy brain. Before Einstein, physicists had a huge problem on their hands. Experiments like the famous Michelson-Morley experiment in 1887 were trying to detect ether, a kind of invisible medium through which light was supposed to travel, like air for sound. But no matter how they measured, They found no difference in light speed, even when Earth was moving through space. It didn't matter what direction you went, light didn't care. This baffled scientists and set the stage for Einstein's revelation. Einstein came along and basically said, maybe there is no ether, maybe light just doesn't need a medium, and maybe, just maybe, time and space themselves have to stretch to make this make sense. Bold move, Einstein. Very on brand. Now for a delightful fringe fact, did you know your own eyes actually delay the light signals they receive by a few milliseconds? Your brain compensates by adjusting what you see to align with where things should be. You're not seeing the present moment, you're seeing a corrected, slightly delayed version of reality, and you never even notice. So technically, your perception is already bending time in microdoses, just to keep you upright and not walking into doorknobs. Historians still argue whether Einstein's simplicity, the refusal to invent new substances like ether, was what truly cracked the code, or whether the math was just inevitable. Either way, it changed everything. The light clock isn't just a metaphor, it's a truth wrapped in a thought experiment, and it explains why moving fast means experiencing less time. Let's bring it back to Earth. Picture a rocket now, a big, gleaming, totally not built by Tesla rocket. You're sitting inside, accelerating close to the speed of light. From your point of view, nothing feels strange. Your light clock ticks steadily, your sandwich tastes fine, and your playlist sounds just as mediocre as usual. But to someone watching from Earth, your light clock has gone sluggish. The time between ticks has stretched, and since everything on your rocket is following that same timeline, including your biological processes, you're aging slower from their perspective. Not because of magic, not because of camera tricks, just because you're moving fast and light refuses to budge. Here's something beautiful. The closer you get to the speed of light, the more extreme this effect becomes. Time doesn't just slow down, it nearly stops. If you could somehow hit light speed, spoiler, you can't unless you're a massless particle. Time would freeze entirely and distance would shrink to zero. Every point in space would flatten to a single infinite moment. Weird, right? Light doesn't experience time. That photon you imagined earlier, it was emitted from a distant star 1 billion years ago. But from the photon's point of view, it left and arrived in the same instant. No time passed at all. For light, the universe is one endless, motionless flash. And you're just a slow creature made of meat forever crawling through time like it's molasses. How rude. So tonight, as you tuck yourself in and imagine those little photons bouncing between mirrors in the dark, just know, the speed of light is more than a number. It's the iron wall at the edge of your reality, and time, the one thing you thought was steady, bows to it without complaint. Tick, pong, tock, ping. The little light keeps bouncing, and with every bounce your understanding of time gets just a little more sideways. Now let's meet the twins. Not your average pair, mind you. These two are the stars of one of physics' most mischievous mindbenders, the twin paradox. And while this scenario has never actually been tested with real, living twins, yet, it's become the go-to thought experiment for understanding how time dilation plays out in the real world, or at least the real world according to Einstein. So here you are, standing in the kitchen with your identical twin. You've got the same genes, same laugh, same tragic haircut from the 4th grade. But today, something's different. You've decided to become a space traveller. Not the gentle kind that floats around in Earth's orbit sipping from Capri Sun pouches. No, you're signing up for the high-speed, near-light-speed kind of trip, the kind of ride that makes even time nervous. Your twin stays behind on Earth, possibly opening a moderately successful bakery. You, meanwhile, hop into a spaceship designed to reach speeds that brush up against the cosmic speed limit. The engines roar and off you go, accelerating into deep space at 99.999% the speed of light. Time on board begins to behave oddly. To you, everything feels normal. You blink, breathe, snack on space granola, but unbeknownst to you, the clock back on Earth is doing something different. Faster, much faster. Because while you zip through the cosmos, your time has slowed down compared to your twins. Years pass on Earth. Big years. Elections, ice cream flavours, apocalypses. Meanwhile, only a fraction of that time has passed for you. You turn the ship around, head home, and land. Probably expecting your sibling to be just a little older than you. Except they're ancient, wrinkled, retired, possibly giving out hard candies to kids who don't even know what DVDs were. And you're still young, time barely touched you. You've pulled off the greatest anti-aging trick in human history, and all you had to do was leave the planet at relativistic speeds. Now let's be clear, this is not science fiction. The math behind it checks out. The paradox is only a paradox in name. It actually has a pretty solid explanation. You and your twin started in the same place, but only one of you underwent acceleration and deceleration, which breaks the symmetry. That's the key. Your twin stayed in one inertial frame, Earth, while you changed frames by zooming out and then turning around. It's kind of like if one person stands still while the other runs a marathon, and afterward they argue about who's more tired. It's not just about speed, it's about who had to push through the shift in reference frames, and that was you. Historical fact incoming. Paul Langevin, a French physicist, first introduced this idea in 1911, just 6 years after Einstein's special relativity hit the scene. Langevin wasn't describing real astronauts yet, they didn't exist, but he was already imagining future humans zipping through the stars and returning to Earth as time-travelling tourists. Historians still argue whether the twin paradox is a perfect model. Some say it oversimplifies the complexity of acceleration and frame switching. Others argue it's ideal for classroom use but misleading in cosmic terms. Either way, it gets people thinking, and that's half the job of physics. So here's your quirky tidbit to chew on. If you really want to maximize the twin paradox, forget rockets. Find a black hole. Hovering just above its event horizon would slow your time dramatically compared to someone far away. You could watch the universe's future unfold in fast forward, all while barely aging. That's relativity's darkest little time machine. But back to you and your twin. Now that you've returned, the emotional side kicks in. They've lived a whole life. You've only lived a few years. How do you even begin to relate? What do you talk about? Your memories are out of sync. Their favourite songs are from a decade that hasn't even happened for you. You feel like a visitor from the past, or maybe they feel like a ghost from the future. Time dilation doesn't just bend clocks, it bends relationships. And suddenly it hits you. Time is not universal. Your twin's time was theirs and yours was yours, and there's no cosmic judge to say which one was right. They're both right. That's relativity. You can almost hear the universe chuckle in the background, whispering, "There's no such thing as a single now." This whole thing rattles the Newtonian idea of a synchronized universe. Newton imagined time like an invisible stage on which all things danced, a shared rhythm, beating the same for stars and snails. But Einstein, he tore up the script and handed everyone their own metronome. Your time is your time, and it can stretch or shrink depending on your motion through space-time. Oh, and here's one more layer to stack on your sleepy brain. According to relativity simultaneity, two events happening at the same time is also relative. Two people moving at different speeds might disagree on whether two lightning bolts struck simultaneously. They'd both be right, in their own frames. There's no absolute now to anchor things. The implications, well, aside from ruining dinner plans across the galaxy, it means that time isn't a river. It's more like a big twisty jello mold, wobbling differently for everyone. So as you drift towards sleep, think of that spaceship version of yourself, skimming the edge of a light speed, watching stars blur into smears. The seconds are long, the years are short, and somewhere on Earth, your twin story unfolds without you. And when you finally meet again, maybe you'll just smile and say, "You haven't changed a bit," even if they have. You step off the spaceship now, older by a few years, sure, but decades younger than your twin, who's already eyeing retirement brochures. Your boots crunch against Earth's soil again, and even though everything looks familiar, time itself feels unfamiliar. As if the rules you knew all your life only applied when you weren't moving at 1,000,000 kilometers per hour. You shake your head and glance down at your wrist. Your old loyal watch still ticks, but now you know, it doesn't tick the same for everyone, and that's when it hits you. If time dilates depending on motion and gravity, how the heck does anything work? How do we coordinate flights, synchronize digital networks, keep the world turning in perfect rhythm when everyone's clock is doing its own private jazz solo? The answer is, relativity isn't just theoretical, it's baked into everyday life. Let's take your GPS for a spin. You open the map on your phone to find the closest ramen spot. Yes, it's always ramen. That little blue dot? It's pulled from satellites orbiting over 20,000 kilometers above you. Each one of those satellites is moving at around 14,000 kilometers per hour. Now here's the problem. Because of time dilation, those satellite clocks tick differently than the clocks here on Earth. Faster, actually, thanks to the combination of their high speeds and their distance from Earth's gravitational well. If you didn't correct for those relativistic effects, your GPS wouldn't just drop you off a few meters away, it would be off by kilometers. Every single day, you'd ask for ramen and end up in a tire shop in a different city. So engineers, very patiently, very quietly, build Einstein's equations into the GPS software. The satellites are equipped with atomic clocks, and their time is continuously adjusted to account for both special relativity due to their speed and general relativity, due to weaker gravity in orbit. It's like having a universal translator for time. Historical fact for the insomniac scholar. The GPS system was developed by the US Department of Defense in the 1970s and became fully operational by the 1990s. From the beginning, engineers realized that ignoring Einstein's equations would result in enormous navigation errors. In fact, if you left relativity out, your GPS would drift by about 10 kilometers a day. That's not just inconvenient, it's catastrophic if you're, say, flying a plane or navigating an autonomous vehicle. Quirky tidbit time. Back in the early days of GPS, some engineers who were still skeptical of relativity wanted to test it out before committing to building it into the system. Spoiler alert, they ran a few simulations without the corrections, watched the whole system spiral into useless chaos, and quickly became believers. So yeah, Einstein is in your phone. He's behind the wheel of every Uber. He's baked into the satellite constellations spinning above your head right now, their clocks ticking slightly off beat so yours can stay on track. Let's zoom in a little further. Commercial jets also experience time dilation, albeit minuscule. Clocks on board planes tick a teensy bit slower than those on the ground. We're talking nanoseconds here, but it's real, and it's measurable. In fact, researchers have flown atomic clocks on high-altitude aircraft and brought them back to compare with clocks on Earth, confirming once again, motion messes with time. Historians still argue whether these airborne experiments were more symbolic than scientific, especially in the early days. After all, the time differences were tiny and the instruments weren't always perfect. But over the decades, the evidence became overwhelming and undeniable. Relativity wasn't just a clever idea, it was a functional necessity. Now here's a sleepy what-if for your brain. Imagine a high-speed transit system crisscrossing the globe at near light speed. Cities connected by maglev trains that curve along the edge of time dilation. You step into a capsule in Los Angeles and by the time you reach Tokyo, your watch says it took 10 minutes, but your friends back home say you were gone for an hour. No, we don't have that yet. But if we ever did, your ticket would come with a time adjustment clause. Even now, though, your experience of time isn't quite your own. It's been coordinated, calibrated, corrected. Time servers adjust for relativistic shifts. Atomic clocks tick in volts, whispering to each other over fiber optic networks. The whole world, your alarms, your texts, your digital meetings that could have been emails, only works because we've bent time into submission. And still, it flexes. You take a moment to marvel at that. All those ancient philosophers and scientists who thought time was fixed, like sand falling through an hourglass. And yet, here we are, living in a world where our machines account for Einstein's bending clock every single second. And you wonder, if motion affects time, and you're always moving, spinning with the Earth, orbiting the Sun, hurtling through the galaxy, whose time are you even living in? Well, yours. Relativity doesn't mean time is fake. It just means it's local. Your seconds belong to you. Your watch doesn't lie. It just tells a truth that applies to your little pocket of space-time. Everyone else? They've got their own clocks, their own truths, and occasionally we all agree just enough to share a meal, catch a train, or crash the same Zoom call. So tonight, when you glance at your phone one last time before bed, just remember that time on your lock screen. It's been triple-checked against orbiting atomic clocks. It's been filtered through Einstein's equations. It's the closest thing to a universal now we can muster. And even then, it's still yours alone. Now that you've let GPS satellites and commercial planes subtly warp your trust in time, let's climb a little higher. Actually, a lot higher. You're stepping into the realm of space-time experiments. Not thought experiments anymore, but the real deal, physics lab, grant-funded kind. Tonight's pillow-stuffed mission, tracking down actual clocks that have really bent time. First stop, orbit. Way back in the 1970s, long before you had 10 alarm clocks snoozing on your phone, physicists were already sending ultra-precise atomic clocks into the sky to test relativity. One of the most famous early demonstrations, that charming little test called the Haffler-Keating experiment. 2 scientists took 4 synchronized atomic clocks, placed them on commercial jets, and flew them around the world. 1 set eastward, 1 set westward, and a reference clock stayed grounded at the US Naval Observatory like a loyal time butler. The result? You guessed it. The airborne clocks didn't agree with the earthbound one. Time dilation had occurred. The eastbound plane, moving in the direction of Earth's spin, lost a tiny bit of time. The westbound one, moving against Earth's rotation, gained some. Tiny amounts, of course, but measurable. Real. Physics doing its slow dance in the sky. You lean into your pillow a little more. That was 1971. Since then, the experiments have gotten sleeker, faster, colder, and way more expensive. Fast forward to the Gravity Probe, a mission in 1976. Not as famous as Apollo, not nearly as catchy a name, but still a milestone. NASA launched a hydrogen master clock into suborbital flight. Basically, a very expensive wristwatch strapped to a rocket. At 10,000 kilometers up, it ticked faster than an identical clock on Earth, just as Einstein's general relativity predicted. Less gravity, faster time. And the difference? A whopping 4 parts in 10 billion. You could run that clock for 3,000 years before it got a full second ahead. Not exactly dramatic, but then again, physics rarely wears glitter. Here's a quirky tidbit to tuck into your dreams. In 2010, physicists at the National Institute of Standards and Technology, NIST, managed to detect time dilation caused by just a 33 centimeter change in height. That's the length of a ruler. They placed 2 aluminum ion clocks on top of each other, separated by a foot, and found, very delicately, that the lower clock ticked slightly slower due to Earth's stronger gravity at that height. So yes, if you sleep on the top bunk, you technically age faster than your roommate. Good luck using that to win an argument. Historians still argue whether the Haffler-Keating experiment was definitive proof or just experimental flair, especially given the limitations of 1970s technology. The measurements were tiny and noisy, and some data required post-flight adjustments. But almost everyone agrees it pointed the way. The general shape of time's weirdness had become undeniable. Let's slow down for a moment. You're lying in bed. A soft breeze creeps through your window. Outside, the stars are doing their silent dance. Somewhere far above, satellites are ticking along with their own tiny distortions. Time is warping all around you, and yet it feels smooth, continuous. But that's the trick. Time dilation is gentle, almost romantic unless you push the extremes. Want to really feel it? Go faster, way faster. At the European Organisation for Nuclear Research, yes, CERN, the Large Hadron Collider accelerates protons to 99.9999991% the speed of light. Those little particles, when standing still, would decay in microseconds. But at those speeds, their internal clocks slow down. From our earthbound perspective, they live longer. Their decay is delayed. Not because anything changed inside them, but because their journey through time has shifted. That's the thing. Even subatomic particles obey relativity. Even particles that don't know what day it is are bending the rules of the calendar. And in case you're wondering whether this time-stretching magic only happens on Earth, nope. It's everywhere. In space, time dilation isn't rare, it's the default. Let's hop into a satellite orbiting a neutron star, a city-sized ball of collapsed matter spinning hundreds of times per second. Its gravity is so strong that the difference in time between the surface and orbit becomes dramatic. If you could hover just above its crust, and, survive the intense radiation and death vortex, you'd experience minutes while your friends in orbit would watch hours pass. Black holes? Oh, we're saving them for later. They're a whole other bedtime monster. For now, just know this. We've proven Einstein right. Not once, not with a shrug, but repeatedly with atomic clocks, satellites, ion traps, and high-speed jets. Time does stretch, it does slow down, and the universe has been whispering this truth to us for decades, but it only whispers. The effects are subtle, like the way your skin knows it's autumn before your calendar does. Unless you're hurtling through space at insane speeds, or plunging into a gravity well, you won't feel time bending, but it's there, always, hiding behind your heartbeat. So tonight, as you lie still while the Earth spins at 1,000 miles per hour and orbits the Sun at 67,000 miles per hour, know that motion, that movement, is slightly altering your personal clock, not enough to skip your morning alarm, but enough to remind you time is not a constant. It's a conversation between motion and gravity, between clocks and cosmos, between you and everything else. And somewhere, an atomic clock ticks in a vacuum chamber, precise to within a billionth of a second, just waiting to be outdone. You open your eyes inside a spacecraft again. No, not a dreamy, gentle orbit like before. This one is fast, very fast. The kind of fast that makes physics start coughing nervously and pointing at the emergency equations. You're not just travelling at impressive speeds now, you're creeping up on the cosmic speed limit. And that's the part most people miss when they first dip their toe into the puddle of relativity. There is a maximum speed in the universe, and that speed is light. Not because we haven't built a big enough engine yet, not because of air resistance, but because the laws of physics literally won't let anything with mass, like you or your favourite snack, ever hit that speed. Let's break it down. You start accelerating. At first, things feel normal. The stars smear slightly in the window. Your body adjusts to the G-forces. Your coffee cup slides dramatically across the console because you forgot to secure it, again. As you push toward 90% of the speed of light, weird things begin to happen. Your mass increases. No, not in the ate too many freeze-dried burritos way, but in a very real, relativistic way. To an outside observer, you're getting heavier, not bulkier, just harder to push. The faster you go, the more energy it takes to increase your speed even a tiny bit. By the time you hit 99.9% light speed, adding more thrust gives you less and less return. You're pushing against the very structure of space-time itself, and time, it's dragging like a tired puppy. Back on Earth, hours and days are passing. Birthdays, sunrises, new Taylor Swift albums, just sailing by. But inside your ship, the seconds feel normal. Your light clock ticks calmly between the mirrors, but from Earth's perspective, your time has nearly stopped. If you kept accelerating, you could cross galaxies and return home in what feels like days to you, while millennia pass for everyone else. So let's say you could push the engines harder, fuel be damned. You're now at 99.999999% the speed of light. You peek back at Earth, and, from your point of view, it looks like it's spinning in fast forward. Cities rise and fall, oceans boil and freeze, civilization hiccups through epochs. Time dilation doesn't just slow you down, it compresses the universe around you. And if you could somehow, impossibly, reach light speed, well, space-time breaks down entirely. Your mass becomes infinite. Your energy requirements become infinite. Time itself becomes undefined. You don't just hit a speed limit, you hit the speed wall. Mainstream historical pause. Physicists first noticed this curious asymptotic behaviour in the early 20th century. When they began working with electrons and high-speed particles, they saw that energy increases didn't linearly increase speed. Instead, velocity asymptotically approached c, the speed of light. Every push added more energy, but less speed. Einstein's equations didn't just predict this, they explained it. Historians still argue whether this speed limit is a fundamental property of reality, or just a side effect of our current model of physics. Some fringe theorists suggest that under extreme conditions, like quantum foam or wormholes, the limit could be bent or even sidestepped. But so far, light is the line in the sand. And here's your delightfully strange fringe tidbit, tachyons. Ah, yes, tachyons, hypothetical particles that always move faster than light. They pop up in some equations like uninvited guests. According to theory, they can't slow down to light speed any more than we can speed up to it. They'd experience time backwards too, which opens up a messy drawer of paradoxes, including the possibility of violating causality. That's right, faster than light travel might mean seeing the effect before the cause. Congratulations, your spaceship exploded before you launched it. Of course, tachyons have never been observed. They're more like mathematical cryptids, useful in theory, dubious in reality. Still, they keep sneaking into textbooks, like Bigfoot in a lab coat. So why does this speed limit matter? Why should your sleepy brain care? Because the closer you get to light speed, the more pronounced time dilation becomes. At pedestrian speeds, Cars, planes, even rockets, it's just a whisper. But once you edge into relativistic territory, the whisper becomes a roar. Physics doesn't gently suggest you slow down, it demands it. That's why every sci-fi story with ships travelling at light speed without relativistic effects is, well, fiction. If Han Solo really made the Kessel Run at 99.999% light speed, he'd arrive to find the Empire a pile of galactic dust and the rebellion turned into a museum exhibit. And Chewbacca would be stuck explaining the time dilation to customs. You roll over slightly now, imagining your own starship quietly slicing through the void. Inside, your heart beats gently. Your food tray floats lazily beside you. Everything feels still. But outside, the universe is racing. Galaxies drift like slow smoke. And time, it's on pause, for you. That's the paradox of high-speed travel. You can't feel the dilation from inside. Your experience of time stays steady. But the outside world moves on, like a fast-forwarding VHS tape. Ask your parents what that is. In relativity, there's no universal clock ticking away, just your own, ticking slower and slower, while the universe forgets you ever left. So maybe that's why light is the limit. Not because nature hates speed, but because the fabric of time itself would unravel past that threshold. At light speed, distance collapses. Time vanishes. You wouldn't travel through space. You'd skip across it in a single flash like light does. No time, no aging, no delay. But you'd also cease to experience anything at all. Because light doesn't experience time. Let that sink in as you listen to the soft hush of night around you. The universe isn't being difficult, it's being precise. The speed limit isn't a barrier, it's a safeguard. A cosmic reminder that time and motion are bound together, dancing cheek to cheek, forever in step but never in sync. And as your ship slows to sublight speed again, maybe just enough to wave at the rings of Saturn, you realize something humbling. You're not designed to outrun time, you're designed to feel it. Let's get cozy now, not in a spaceship, not in a particle collider, but right here in your living room. Or maybe the floor of your childhood bedroom where you once tried to teach your dog the difference between fetch and physics. Spoiler, the dog did not care, but tonight you care. Because we're going to reimagine time dilation from scratch. No PhD required. Let's call this the Time Dilation for Dummies and Dogs Edition. And yes, the dog gets a starring role. Picture this. You've got 2 golden retrievers. One of them is extremely chill, curled up on a fuzzy blanket, snoring gently through the afternoon. The other? A curious pup you've strapped into a shiny little rocket. Don't worry, this is a very humane, very hypothetical rocket, and you launch them into orbit. Fast forward a few months, the rocket returns. Both dogs are wagging their tails, thrilled to be reunited, but there's a difference. The space dog is slightly younger than the earthbound one. Not enough to cancel a vet appointment, but just enough to make every physicist within a 10-mile radius start muttering about clocks and velocity and general relativity. That's time dilation, but with dogs. And it's real. You don't have to go far to feel it either. Even commercial airplane pilots, real humans, not canines, experience a whisper of this. Their watches tick just slightly slower than the folks waiting at the baggage carousel below. It's not dramatic, but it's measurable. The world's most precise atomic clocks confirm this again and again. If you move faster, you age slower compared to someone who stayed still. It's not an opinion. It's not a metaphor. It's baked into the universe like sugar in a cookie. Here's a weird little fringe fact to toss your way. If you had a twin and you each owned a private jet, must be nice, and you flew in opposite directions around the world long enough, you'd come back to find your ages mismatched. Slightly, but still, enough to annoy whoever's older by a few microseconds. Historians still argue whether the everyday relativity angle, planes, clocks, dogs, cheapens the theory's grandeur or helps make it accessible. Some traditionalists want relativity reserved for black holes and starships. Others believe that grounding it in the familiar is the whole point. Personally, I think Einstein would have adored the dog example. He was a cat person, but still. Now, let's zoom out for a second. You've been imagining time as a kind of invisible river flowing past us, steadily, calmly, equally for all things. But that's the Newtonian idea of time, simple, comforting, and entirely wrong. Einstein shattered that comfort with the idea of relative time. It's not the river that flows, it's you, moving through the fabric of space and time. and your speed changes how much of the river you experience. The faster you go, the more you tilt your trajectory through space-time. You spend more of your motion budget on space, which means you spend less on time. It's like balancing a cosmic checking account. Speed robs you of time, rest returns it. So think about that next time your dog is racing in circles while you just sit on the couch watching. That dog, aging slower. Probably not enough to skip a birthday, but still. And it's not just velocity that bends time, gravity does it too, but that's for another section. For now, let's stay in motion. Imagine you're on a treadmill. As you speed up, everything else around you seems to change more slowly. Your music, the wall clock, that guy in the corner who's somehow sweating and texting at the same time. In relativity, this treadmill isn't just giving you cardio, it's giving you temporal leverage. Speed warps time, period. Even your perception starts to shift if you go fast enough. At high velocities, length contraction kicks in. That's the lesser-known cousin of time dilation. Not only does time slow for you, but distances actually shrink in the direction of motion. You don't feel it internally, but from the outside, someone watching you zipping along sees your spacecraft squish ever so slightly. It's space-time doing origami. And before you start accusing the universe of gaslighting you, remember, it's consistent. Everyone's version of reality agrees with Einstein's math, even if it contradicts what they thought time was supposed to do. Now here's a thought to make you blink a few extra times before sleep. You already live with a time bubble around you. That's right. Even now, sitting still, your body is experiencing a slightly different rate of time than someone standing a few feet away, if they're at a different elevation or moving at a different pace. It's small, yes, but it's there, like a personal timestamp written into your atoms. You're not just existing in time, you're dragging it along with you, reshaping it just by moving. So go ahead, imagine strapping your dog into a rocket again. Just be sure to bring a matching spacesuit this time. As the rocket climbs into orbit, your pup starts to diverge in time. Not much, just a tick, just a whisper. But a whisper loud enough for Einstein to hear from the afterlife. And when they return, you'll still scratch their ears, still feed them kibble, still laugh when they bark at nothing in particular, but you'll know something they don't. They've aged less than you. They've drifted just a little, gently, away from your time. And the universe smiled quietly and said, "Yup, that's how it's always been." You blink and suddenly the stars are bending. Not because you're dizzy or sleep deprived, though let's be honest, maybe a little, but because you're drifting, slowly, carefully, toward the edge of something that doesn't just bend time. It consumes it. You're approaching a black hole now. Not too close. Not yet. Just close enough to feel reality start to twitch. Out here, the rules of gravity and time aren't merely suggestions. They're dominant forces squeezing space like a stress ball and stretching time like old chewing gum. This is where gravity's grip on the hourglass becomes undeniable. In everyday life, gravity just pulls things downward. Apples, wallets, your phone after you drop it face down. But Einstein said gravity is something far deeper, something that warps space-time itself. The more massive an object, the more it bends that fabric, and the closer you get to it, the slower your time runs compared to someone farther away. This isn't just theory, it's been measured. But we're going to skip the mountaintop experiments and dive headfirst into the cosmic deep end. You're falling toward a black hole. Don't panic, we're in imagination land. Nothing sticky yet. You're in a sleek observation pod drifting ever closer to the event horizon, the boundary around a black hole where time and space start doing their weirdest tango. Inside this boundary, nothing escapes. Not light, not radio waves, not even your awkward attempt at a goodbye text. But just outside it, that's where the magic happens. From your perspective inside the pod, everything feels fine. Time ticks along normally. Your breathing is steady, the instruments still beep. But your friend back on the space station, watching through a telescope, sees something very different. Your time appears to slow down. They see your pod drifting slower and slower, your movements becoming syrupy, sluggish, as if the black hole were pulling on your seconds, not just your body. And just before you cross the event horizon, your friend sees you freeze. Literally. To them, you never quite fall in. You just pause there, indefinitely, fading into a red-shifted blur. From their frame of reference, time stopped for you. But from your point of view, you fall right through, and that, right there, is the crown jewel of time dilation. The closer you get to an immense gravitational source, the slower your time runs compared to someone farther away. In the extreme environment of a black hole, this difference becomes infinite. Historical sidebar to lull you deeper. This was one of the core predictions of Einstein's general theory of relativity, published in 1915. While special relativity showed that time depends on speed, general relativity added gravity to the mix. It wasn't just motion warping time, it was mass. And no mass warps quite like a black hole. Decades later, this theory was beautifully confirmed. One of the most elegant validations? The 2015 detection of gravitational waves, ripples in space-time caused by colliding black holes. We literally heard the universe stretch. And we confirmed, once again, that Einstein's equations weren't just bedtime stories. They were blueprints, quirky tidbit for your cosmic scrapbook. There's a region just outside a black hole called the photon sphere, where light can orbit the black hole in perfect circles. It's like a racetrack for photons. Go too fast or too slow and you spiral in or out. But if you hit the sweet spot, you're literally riding light around a hole in space-time. Historians still argue whether we'll ever get close enough to a black hole to experience this firsthand. The nearest candidate, Sagittarius A star, sits at the centre of our galaxy, about 27,000 light-years away. But in 2019, scientists with the Event Horizon Telescope did manage to image a black hole's shadow in a galaxy far, far away. So yes, we're not just dreaming about this stuff, we're looking right at it. Now imagine building a base near the edge of a black hole, one designed not to fall in but to hover just close enough. You live there for a year, time drips by like molasses. You read books, water a weird little space cactus, maybe write that novel you keep threatening to start. Then you return to Earth, and everyone you knew is gone, not mysteriously, just older. Generations older. Your 1 year near the event horizon stretched into centuries for those back home. Your sleepy sabbatical has become an unintentional time jump. And here's where it gets deeply emotional in that gentle existential way. Time dilation isn't just physics, it's separation. It's what happens when two people live different timelines not because of life choices, but because the universe physically won't let them age together. You think about this as your pod drifts closer to the black hole. You're not falling in, just floating close, watching light stretch, watching time bend. This is the extreme edge of Einstein's theory, where space folds and time begins to resemble taffy. Out here the rules are strict, the consequences sharp, but they're the same rules that govern the clocks on Earth, same math, just amplified. So next time you feel like time's flying or dragging, remember that your perception can stretch, but it can never quite match someone else's. Not if they're moving, not if they're higher or lower, not if they're near a black hole. Everyone's clock is a little bit private, and yours, still ticking, still whispering, still yours. You drift now, slowly, away from the black hole, back towards safer space-time. The distortion fades, the stars realign, and the silence becomes less heavy. But something's changed. You're carrying that experience of slowed time, stretched seconds, the strange intimacy of existing on a different tempo than the rest of the universe. So what happens next? Well, what happens inside your mind? See, time dilation isn't just an effect on clocks and satellites and science fiction spaceships. It's also a lived experience. And tonight, we're diving into the oddly squishy topic of your brain on time warp, how time feels, how memory cheats, and why our inner clocks sometimes beat out of sync with the cosmos. Let's start with a question that's deceptively simple. Have you ever felt like time slowed down during a crisis? You know the moment. A car swerves, your phone slips, a bee flies suspiciously close to your eye, and suddenly you're hyper-aware. Your perception goes widescreen. Every second stretches out like taffy. You react faster than you thought you could. Later, when you replay the scene in your mind, it feels like it happened in slow motion. But here's the twist. Time didn't actually slow down. You did. Or rather, your perception did. Your brain, in moments of high adrenaline, ramps up its processing power. It encodes more detail, takes in more sensory information, and shoves it into short-term memory at a much higher density. When you look back on that memory, it feels longer because there's more of it. More data per second. Like a high frame rate video played at normal speed, it feels richer, slower, more intense. So in a strange subjective way, you experience time dilation. No relativity equations required, just a brain doing its best to keep you alive. Historical fact for the dreamers. This phenomenon was first studied seriously in the 2000s. Researchers at Baylor College of Medicine conducted freefall experiments with human subjects, in controlled environments of course, not just pushing people off buildings. They found that people didn't actually perceive time more slowly in real time, but they remembered those moments as lasting longer. The dilation wasn't external, it was cognitive. Quirky side fact. Some people experience this sort of internal dilation frequently. Certain neurological conditions like epilepsy, schizophrenia, or extreme migraines can warp time perception dramatically. Minutes can feel like hours. Hours can collapse into blinks. It's a reminder that time, at least as we experience it, is often more suggestion than certainty. Historians still argue whether our subjective sense of time was shaped more by survival instincts or by social structures, like calendars, rituals, or the crushing realization that Monday exists. Either way, your brain has never been a perfect clock. It's more of a squishy, creative estimate machine, constantly guessing and smoothing and compressing the timeline of your life. And here's where things get extra dreamy. Imagine you actually underwent high-speed time dilation. Say, you took that round trip to a black hole and returned home a century later. Your body's clock has only ticked a few years, but your brain, well, it's wired for Earth time. Circadian rhythms, sunrise and sunset, the scent of coffee at 7 a.m. Suddenly you're in a world that's fast-forwarded without you. Time isn't just different, it feels wrong. You're out of sync, not just biologically, but emotionally. The seasons feel weird. The tempo of conversation, of daily routines, of social norms, all sped up. Even without relativistic travel, we experience this kind of psychological time displacement. Think about jet lag, or waking from a long, vivid nap and not knowing what day it is, or emerging from a long illness, or a depressive episode, or just the weird, timeless haze of a pandemic lockdown. Your body is here, your mind's clock is somewhere else, and suddenly you're Einstein's paradox, inside your own head. Let's not forget dreams. Ah yes, dreams. The OG time travelers. You can dream a whole adventure in the span of a few minutes. A full narrative, a rising action, a plot twist. Maybe even a romantic subplot with someone who suspiciously resembles your high school crush. And yet, the EEG scan shows you've only been in REM sleep for a couple of minutes. How? Your brain simply plays with the pacing, like a film editor cutting scenes to fit into a tight schedule. Time stretches and contracts, loops and jumps. In your dream, you never question the clock, because you don't need one. Time in the mind is fluid. And here's a fringe tidbit that'll keep you cozy and curious. Some scientists believe we might someday simulate time dilation in virtual reality. Imagine a high-speed training module where your brain is tricked into perceiving time more slowly, more time to react, more time to think. It wouldn't change the actual clock, but it might feel like it. A DIY relativity, without leaving the room. So what does all this mean for you? It means that while Einstein gave us the equations, your brain has been running its own version of time dilation all along. When you're bored, time crawls. When you're in flow, time vanishes. When you're in love, or in fear, or on the edge of something unforgettable, time becomes elastic. And that elasticity, that subjectivity, isn't a flaw, it's a feature. A beautiful, maddening, utterly human feature. Because time, for all its mathematical precision, is still experienced through a heartbeat, through memory, through attention. It's not just seconds on a clock, it's the shape of your days, the rhythm of your emotions, the soundtrack of your mind. So tonight, as you drift off, eyes half-lidded, body wrapped in blankets, dreams waiting just off screen, know this. You're not just moving through time. Time is moving through you, bending around your senses, reshaping itself based on how you feel, what you remember, and where your mind decides to go next. And no matter what the universe says with its equations, your perception will always bend the clock your way. Now let's get a little reckless. You've earned it. After all, you've survived high-speed rockets, orbiting dogs, frozen time near black holes, and the daily existential dread of realizing your microwave's clock isn't even right. So tonight, you pack your sense of curiosity and step into something far more dangerous and far more fun: time tourism. Let's say, just for the sake of sleepless science fiction, that you want to travel through time. Not in the I remember what lunch tasted like sense, but actually, physically, observably. You want to cheat the calendar, see the year 3000, maybe wave at your own birth. possibly dodge a few awkward social engagements in between. Is that even possible? Well, kind of. But also, not really. Let's start with what does work. You already know from the past 10 sections that travelling fast or getting near massive gravitational fields slows your experience of time. So yes, you can go forward in time just by taking advantage of good old-fashioned relativity. Ride a ship near light speed, spend a year on board, and return to find Earth has aged decades, or more. That's not hypothetical, it's physics. Boring, consistent, proven physics. So if you're a fan of one-way time travel into the future, good news. Relativity has your back. No DeLorean, no flux capacitor, no paradox. Just acceleration, time dilation, and a lot of snacks. But going backward, that's where things get messy and deliciously impossible. You see, our current understanding of physics doesn't really allow for backward time travel without also breaking causality. The sacred law that says cause comes before effect. Spill your coffee, then cry about it, not the other way round. That sort of thing. Still, let's play. There's a concept in physics called a closed time-like curve. It's a solution to Einstein's field equations that, in theory, would allow you to loop through space-time and return to an earlier moment. Sort of like running laps around a track made of time. Exotic, weird, entirely speculative. Where do you find these curves? Glad you asked. Enter the wormhole. Also known as an Einstein-Rosen bridge, which sounds like a toll booth between galaxies, a wormhole is a theoretical shortcut through space-time. Picture 2 points in the universe connected by a tunnel. You step into one end and pop out somewhere else, possibly in a different time, not just a different place. Now, no one's actually found a wormhole, but the math doesn't forbid them. Some solutions to general relativity suggest they could exist. The problem is keeping them stable. You'd need something called exotic matter with negative energy density to hold the throat of the wormhole open. Otherwise, it collapses faster than your willpower at 2 a.m. near the fridge. Quirky tidbit time. In 1988, physicist Kip Thorne and his colleagues proposed a scenario where a traversable wormhole could allow for backward time travel, if one mouth were accelerated to near light speed and then brought back. Thanks to time dilation, one end of the wormhole would be younger than the other. Step through the older mouth, and you'd emerge in the past. Voila! Physics-based time machine. Historians still argue whether Thorne's model was a real possibility or just a clever way to scare his grad students, but the math works. The physics, while speculative, isn't wrong, just inconvenient. So let's say you build one. You open a wormhole in your garage using your leftover Halloween fog machine and some exotic matter you found on eBay. You accelerate one end to relativistic speeds, bring it back, stabilize the thing with magnetic containment fields powered by, you guessed it, your local coffee shop's Wi-Fi. Now you've got a time machine, a real one. You can't go back to before the wormhole was created. Sorry, no dinosaurs. But you could travel between the mouths and find yourself in 2 different times. So what happens if you go back and, say, prevent yourself from ever building the machine? Ah, yes, the dreaded grandfather paradox. If you travel into the past and change something that prevents your time travel from ever happening, how did you get there in the first place? Cue mental nausea. One proposed solution? The Novikov self-consistency principle. It states that time travel is allowed, but only if your actions in the past are already part of history. So you can't change the past. You were always going to show up. Your interference is already baked into the timeline, which is sort of comforting, and also deeply unsettling. Want a more flexible option? Try the many worlds interpretation. Under this model, going back in time would create a branching timeline, a new universe that splits off from your original one. So yes, you could stop your younger self from buying those ugly shoes, but you wouldn't fix your universe. You just create a new one where your fashion sense is slightly less questionable. So, is time tourism possible? Forward? Yes, by bending time through speed and gravity. Backward? Maybe, if you don't mind abandoning causality, risking paradoxes, and possibly never returning to your own timeline. And even if all the theoretical hurdles were cleared, exotic matter, stability, paradox avoidance, there's one more problem. Time travel might be invisible. Even if someone did go back in time, how would we know? What if they can't interact? What if they're stuck as observers, watching a version of reality that can't see or hear them? What if someone from the year 3022 is watching you right now and cringing at your bedtime playlist? Time travel is a tricky beast. It might be real. It might be fantasy. It might be sitting quietly at the edge of our understanding, waiting for a physicist brave enough to poke it with a stick. But for now, we travel the only way we know how, 1 second at a time, forward. So as you close your eyes, imagine your future self, drifting through wormholes, dodging paradoxes, whispering through closed time-like curves, maybe even circling back to visit this exact moment, right here, right now. And maybe they smile, because for all the years they've crossed, this was the one moment they wanted to see again. You're standing on a vast plain of ideas now, 2 great figures looming in the distance like dueling statues carved from stardust and stubbornness. One in breeches and powdered wig clutching an apple. The other, a wild-haired thinker in a rumpled coat staring at the sky like it's a broken watch he's trying to reset. Newton versus Einstein. And tonight you get a front row seat to one of the most elegant philosophical smackdowns in the history of science. Absolute time versus relative time. Let's start with Isaac Newton, the 17th century math wizard who invented calculus, deciphered gravity, and basically redefined motion, while still managing to look very disappointed in all his portraits. For Newton, time was absolute, a constant universal background tick-tocking evenly across the entire cosmos. His view was comforting, like a grandfather clock for the universe, always reliable, always steady, never personal. To Newton, it didn't matter where you were in space or what you were doing. A second for you was a second for a comet, a cannonball, or a lonely shepherd on a distant hill. Time marched forward in a perfect rhythm, independent of your experiences or your speed. Historical fact, in his masterpiece Philosophia Naturalis Principia Mathematica, 1687, Newton literally wrote, "Absolute, true, and mathematical time, of itself and from its own nature, flows equably without relation to anything external." Translation: time doesn't care about you, it just is. This idea held up remarkably well. For centuries it was the bedrock of physics and celestial mechanics. Planets moved like clockwork, equations danced in lockstep. The idea of a universal time made everything clean, calculable and comfortingly mechanical. And then along came Albert. And Albert did not like comfort. Einstein saw cracks in Newton's beautiful clockwork. The Michelson-Morley experiment had failed to detect Earth's motion through the so-called ether, a silent hint that maybe, just maybe, time didn't behave the same way for everyone. Maybe time wasn't an invisible stage at all. Maybe time was part of the show. Einstein's special relativity, unleashed in 1905, shattered Newton's concept of time like a teacup under a jackhammer. He proposed that time is relative, not absolute. It changes depending on your speed, your frame of reference, and even your gravitational environment. No universal clock, just lots of little ones, each with its own rhythm. Imagine 2 people moving differently. According to Einstein, not only might they disagree on how long something took, they might disagree on whether 2 things happened at the same time at all. That's the principle of relativity of simultaneity, and it makes Newton's neat timeline start to look like a Picasso painting. You can almost hear Newton's ghost mumbling, "Now wait just a minute," but Einstein wouldn't, because he didn't just break time, he stitched it to space. Suddenly time wasn't a separate floating thing. It was a dimension, woven into the very geometry of the universe. 4 dimensions: length, width, height, and time. Time became local, dependent, flexible. And for the first time, motion and time were married in a way that made physics weep and cheer at the same time. Here's a cheeky fringe tidbit for your dreams. In the early 20th century, when Einstein's ideas started spreading, not everyone welcomed them. Some physicists, and more than a few philosophers, rejected relativity for being too abstract, too weird, too willing to sacrifice intuitiveness for math. One Austrian philosopher, Hans Reichenbach, devoted entire books to explaining why humans struggle to accept relativity. It's just not how we're wired to experience the world. Historians still argue whether Einstein's overthrow of Newton was a full-on coup or more of a strategic update. After all, Newton's laws still work beautifully for most everyday scenarios. Want to calculate the arc of a basketball? Newton's got you. Need to launch a weather balloon? Still Newton. But the moment you approach light speed or enter a strong gravity well, Einstein steps in like a bouncer saying, "You're going to need different math, and here's the most delicious irony. Newton's absolute time still feels right. It's what you experience. Your phone alarm goes off at the same time every morning. Your oven bakes at the same speed whether you're happy or sad. Time, to you, seems absolute. But that's the illusion. Einstein showed that we're all carrying personalized clocks. Your seconds, your minutes, they belong to you, and they aren't guaranteed to match anyone else's. They only sync when conditions are shared, when motion and gravity line up just right. And that idea that every person might live in slightly different time isn't just physics, it's philosophical dynamite. Because it means there's no true now, there's only your now. Think about that. If you and someone on a distant star both look at your watches and agree it's midnight, what does that even mean? If you're moving differently or under different gravity, your timelines are already diverging. You've said now, but you're both already a little out of sync. There is no master clock keeping cosmic time, no universe-wide chime striking the hour, only a tangle of moments flowing slightly differently for each observer, each body, each mind, and yet it all works. Somehow, amidst all this relativistic chaos, we still meet for lunch, still celebrate birthdays, still set timers for pasta, because Newton wasn't wrong, he was just early. His universe was a smooth machine. Einstein's is a wild, flexing, humming web. But both tell parts of the truth. One speaks to the comfort of constancy, the other to the poetry of change. So tonight, as you lie there, not moving but still travelling at 67,000 miles per hour around the sun, remember this: your time is yours. Your seconds are not shared, not cloned, not guaranteed to match anyone else's exactly. They are stitched to your motion, your place in gravity's cradle. You live in a Newtonian illusion, held together by Einstein's invisible threads, and both men, if they were here, would probably agree on one thing. Time may tick in seconds, but it's understood in centuries. You're drifting now, not through space this time, but through something softer, slower. It's the feeling that maybe, just maybe, if you held still long enough, time itself would let you slip beneath it. So tonight we explore what might be the most literal dream of time dilation yet. Sleeping through the centuries. Cryogenic naps, suspended animation, deep dreamy slumber that lets you wake up in a future that doesn't even remember your name. It's the oldest fantasy in the sci-fi survival handbook. If you can't outrun time, maybe you can just sleep through it. Let's lay it out gently. You want to travel into the future, not by accelerating in a rocket or tiptoeing around a black hole, but by curling up inside a chamber, lowering your metabolism to a whisper and pressing pause on your own biology. This is the slow time path, the tortoise in the relativity race, and it starts with cryonics. Cryonics, the process of preserving human bodies, or brains, or entire heads, depending on how dramatic you want to be, at extremely low temperatures after legal death, has been around, in theory, since the 1960s. The idea is simple: freeze now, fix later. Wait for future medicine to wake you up, cure what killed you, and maybe drop you into a future where coffee tastes better and people finally stopped using Comic Sans. But here's the chilly truth. We don't know how to unfreeze people, not without turning them into very expensive, emotionally significant soup. The ice crystals that form during freezing tend to shred cells like a microscopic blender, and while scientists are making progress in vitrification, the glass-like solidification of tissue without crystal formation, it's still far from human-ready. Still, people have tried. There are currently over 400 individuals cryopreserved around the world, mostly in facilities in the US and Russia. They lie in steel tanks filled with liquid nitrogen, waiting, hoping, not aging, not living either. Their time is paused, not through relativistic speed, but through chemical stillness. Now, real-time physics check. This isn't time dilation in the Einsteinian sense, no space-time warping here. But from the sleeper's point of view, it's close. If you could fall asleep without dreaming, without aging, without even a flicker of thought, and then wake up centuries later, it might feel like a jump cut in your own timeline, a personal skip forward. And here's the strange thing. Relativity does allow that sensation. If you spent years at near light speed, your body would experience a very similar thing, just a quiet blink between centuries. The world outside races on. You remain mostly unchanged, distant, disconnected, and yet still here. So cryonics is like faking relativity with biology, a low-tech answer to a high-speed problem. Of course, if freezing sounds uncomfortable, How about slowing down without stopping? Enter suspended animation. This is the gentler cousin of cryonics. Less turn into a popsicle, more hibernate like a bear with excellent life insurance. Scientists have studied how certain animals slow their metabolic processes. Frogs, turtles, even some rodents can reduce their oxygen use and body temperature dramatically to survive harsh environments. The dream is to replicate this in humans, and they're getting close. In some experimental trauma treatments, doctors have successfully induced hypothermic states in patients with severe blood loss, cooling the body to slow metabolic function and buy precious time during surgery. We're talking about clinical death, postponed. There are even studies trying to trigger torpor in humans, a state of near hibernation, not just for emergency medicine, but for space travel. Because here's the real sci-fi goal: interstellar naps. If we ever send people to distant stars, on missions that last decades or centuries, we're going to need more than snacks and crossword puzzles. We'll need to sleep, deeply, for years. Suspended animation, coupled with the time dilation from long-duration space travel, could let astronauts sleep their way into the far future. From their perspective, a gentle rest from Earth's generations passing. And let's be honest, there's a comfort in that idea, that maybe the best way to beat time is not to fight it, or outrun it, or bend it, but to simply opt out for a while. Now here's your fringe tidbit for tonight. In 2000, NASA funded a study on human hibernation for long-term spaceflight, not science fiction. Real money, real research. The study looked at lowering body temperature, reducing muscle atrophy, and even dream management during long-term sleep. The goal, not to freeze people, but to pause them, safely, peacefully, purposefully. Historians still argue whether we'll ever perfect human stasis. Some think it's the key to our future among the stars. Others think it's just another way to avoid accepting that time, however flexible, is still deeply personal, deeply biological. And speaking of personal, what would it mean to wake up in the future? To open your eyes and find your world gone, your friends gone, your family remembered only by history, the seasons different, the sky unfamiliar. Maybe the very rhythm of time, measured, scheduled, lived, completely altered by technology you can't comprehend. Would it be freedom? Or loneliness? Or both? That's the haunting part of time dilation, whether done by physics or by freezing. It moves you forward, but it moves you away. So you tuck yourself in now, a little deeper. You imagine the hiss of nitrogen, the slow blink of cryo chambers, the soft hum of sleeping ships drifting between stars, the stillness of bodies that have escaped the tick of the clock, at least for a while, and you wonder, if I could press pause, would I? Would I skip ahead to the year 2500 just to see what became of us? Would I sleep through the chaos and hope for peace? Would I give up now for later? Or would I stay awake and live the time I'm given? No answer needed tonight. Just drift. Let the clock slow. Let the dreams stretch. Let yourself imagine a world where time can be outrun, not by speed, but by silence. The hum of suspended animation fades behind you now, like a forgotten lullaby. You've dreamt of time travel, bent it through speed, warped it with gravity, and paused it in frozen sleep. But something still lingers, an itch in your sleepy brain. What is time? Not how it bends, not how it ticks, but what is it fundamentally? Let's poke that question gently now, like it's a sleeping cat we're not sure wants to cuddle or bite. Time seems obvious. It's what you measure on clocks. It's what passes while you wait in traffic. It's the thing that makes your cereal go soggy. But the deeper you look, the slipperier it becomes. So tonight, you'll puzzle through one of the biggest and strangest questions in physics. What's real? Time or timing? It starts with the simple things. You remember the past. You anticipate the future. You exist in the present. That seems straightforward, but physics doesn't deal in memory or feelings. Physics only cares about what can be measured, and here's where things go wobbly. According to the most fundamental laws of physics, the ones that govern particles, energy, and motion, there's no special status for now. The equations work perfectly whether time moves forward or backward. They don't care which direction the movie is playing. Flip the reel, and the math still works. This leads us to something deeply weird. Time, in the equations, isn't directional. It has no arrow. It just is, like space. Move left, move right, it's still space. Move forward, move backward, it's still time. But clearly you experience time flowing in one direction. Eggs break but never unbreak. People age but don't de-age. Benjamin Button does not count. We remember the past but never the future. So where's the disconnect? Welcome to the world of the arrow of time. It's not a property of time itself. It's a property of the universe's state. Specifically, it comes from entropy. Ah yes, entropy. The ultimate cosmic buzzkill. In simple terms, entropy is a measure of disorder. According to the second law of thermodynamics, entropy in a closed system always increases. Things go from ordered to disordered, ice melts, stars burn out. Your kitchen becomes a disaster zone if left unsupervised. And that, not time itself, is what gives us the sensation of time flowing. The universe began in a low entropy state, and it's been unravelling ever since. That unravelling gives events their sequence. It gives us before and after. Without it, everything would just exist, static and eternal. Kind of like a storage closet of every possible moment, unorganised and unlabelled. So maybe time isn't something we move through, but something that emerges from change. And here's where the debate truly begins. There are physicists, serious ones mind you, who believe that time is not fundamental, that at the deepest level of reality there is no time, just correlations, patterns, events related by cause and effect, but no universal stopwatch ticking behind the scenes. This idea gets its moment in theories like loop quantum gravity, where space and time are both emergent, woven from even more fundamental building blocks. Think of space-time as a kind of fabric, but zoomed in, it's made of threads. And those threads, they don't come with built-in seconds. One famous proposal comes from physicist Julian Barber, who argues that time is simply an illusion. What we perceive as time is just the movement from one configuration of the universe to another. He calls these configurations nows. We're not moving through time, we're jumping from now to now, like flipping through pages of a flipbook so quickly that it creates the illusion of motion. You blink and wonder, how many nows have I already jumped through just lying here? Historical pause for comfort. Isaac Newton believed time was absolute. Einstein believed time was relative. But Carlo Rovelli, a modern physicist and one of the champions of the time isn't real camp, argues that time might be just a convenient language we use to describe change, not something that exists independently. He compares time to heat. Heat isn't a fundamental thing. It's the collective movement of molecules. We feel warmth, but we're really sensing motion. Maybe time is like that. A sensation, a byproduct of something deeper, not a thing in itself. And this opens a door to a philosophical playground. If time isn't real, if it's not fundamental, then what about the past? Does it still exist? Is the future already there? Are all the moments of your life laid out like pictures on a wall, and you're just walking past them one by one? That's the idea behind the block universe. According to this view, past, present and future all coexist. Time is like a landscape, and your consciousness is just sliding through it, one moment at a time. It's not that moments appear and disappear, it's that they're all there. Always have been, always will be. You're not in time, you are time. Each version of you, each breath, each blink, each heartbeat is fixed in that landscape. Eternal, untouchable. You can't revisit them, but they never vanish. They just are. It's poetic, it's terrifying, it's weirdly comforting. And here's your sleepy little fringe fact for the night. In 2018, a team of quantum physicists suggested that the flow of time might be a matter of perspective, not a fundamental reality. Their experiment showed that two observers could disagree on the order of two events, and both be right. Like watching a movie where the scenes rearrange depending on who's watching. Historians, philosophers and scientists still argue whether time is real, emergent, or entirely a human construction. Some say it's the deepest mystery in physics. Others say we've already answered it and just don't like the answer. But for you, lying in the dark, it all comes down to a quiet question. If time is only a way to measure change, what's really changing? Is it the universe, or is it you? And maybe, just maybe, it's both. So you settle in a little deeper now. The seconds tick, or don't tick, or stretch into something wordless. Whether time is real or just a label doesn't matter in this moment, because you're real. And right now, that's all that counts. You're shrinking now. Not in size, but in scale, slipping down into the world of the ultra-small, where particles pop in and out of existence like moody soap bubbles, and reality is made of probability more than substance. Tonight you enter the realm of high-speed ghosts, short-lived particles that live longer when they move fast. This isn't metaphor, this is experimental proof of time dilation, and it's oddly beautiful. Let's meet our star, the muon, a subatomic particle, kind of like an electron's heavier, more dramatic cousin. Muons are unstable. They decay into other particles very quickly. When created at rest, they last about 2.2 microseconds. That's roughly how long it takes to blink, or almost blink, or think about blinking. But here's where things get interesting. Muons are born in the upper atmosphere when cosmic rays slam into atoms, and endless fireworks show above our heads. These muons then rain down toward Earth, moving close to the speed of light. Now, based on their short lifetime, they shouldn't make it very far. They should decay long before reaching the surface. But they do. They reach the ground, thousands of them, constantly. Why? Because their clocks are running slower. To a muon racing toward Earth at nearly light speed, those 2.2 microseconds stretch out from our point of view. The muon doesn't live longer, it's just that its time is different from ours. From its perspective, it only travels a few hundred meters before decaying. From our perspective, it travels many kilometers. Time dilation, caught in the act. This was first confirmed in 1941 by physicists at Mount Washington. They measured the number of muons arriving at the mountaintop versus sea level and found a surprising survival rate. The math only made sense if time was slowing down for the particles during their rapid descent. Historical moment locked in. Let's pause to appreciate that for a second. Tiny particles, created by exploding atoms in the upper atmosphere, are living longer than they should because they're moving fast. Not a theory, not a thought experiment, just real particles doing what they do with Einstein's equations whispering behind the scenes. Now here's your quirky tidbit to snack on. Researchers at particle accelerators, like CERN, routinely observe this effect. They create unstable particles at incredibly high speeds and watch them last far longer than they would at rest. It's not a glitch, it's the baseline, the reality of how time behaves when you push hard against the light speed limit. If you lived like a muon, if you could move that fast, you too would experience time differently. Minutes for you might be days for the rest of the world. The faster you go, the less you feel time's passing. It's not that you're escaping time, you're just changing your contract with it. Historians still argue whether these high-speed decay experiments were the final nail in the coffin of Newtonian time, or just the most dramatic. But either way, they're among the cleanest confirmations of time dilation we've ever had. And it's oddly poetic, isn't it? That the universe's most fleeting things get to stretch their lives, just by racing through space. Imagine yourself now as a particle, not metaphorically, not philosophically. Really you, reduced down to some minuscule bit of matter flying through a vacuum at 99.99% the speed of light. You don't feel fast, there's no wind, no noise, just stillness inside your tiny frame. But outside, the universe is warping, distances shrink, clocks slow, photons flatten into strange streaks of colour, and you, little particle you, continue zipping forward, living longer than anyone expected. Not because you cheated death, but because time bent around your path. This isn't magic. This is what the universe actually does. It's not just muons either. Any unstable particle, when sped up, gets extra seconds added to its existence from an outside point of view. Physicists even use this trick on purpose to study particles too ephemeral to examine otherwise. They prolong lifespans by pushing particles faster. So in a way, time dilation is a tool, a cosmic loophole, a built-in feature of reality that lets you stretch the unstretchable, if you're brave enough or small enough or energetic enough to chase light. But it also makes you wonder, is time fair? If you can move faster and live longer in the universe's eyes, does that mean time treats everyone differently, based on effort? Or is time simply neutral, bending equally for all who dare challenge it? From the muon's point of view, nothing special happened. It lived its 2.2 microseconds and decayed, just like clockwork. But for us, it became a little time traveller, a particle-shaped proof that time is not what we thought it was, and that's what keeps scientists up at night. Not just the equations, but the implications. If time can be stretched so easily for particles, what else is flexible? If speed grants longevity, what does that say about motion itself? If unstable particles can reach Earth only because of Einstein's rules, what hidden gifts has time dilation given you? You may not be a muon, but you're part of the same universe. You obey the same laws. Your atoms, your heartbeat, your brain, they're all stitched into the same space-time fabric that lets particles bend the clock. So tonight, as you slow your breathing and let your muscles go soft, picture that quiet storm of muons falling invisibly around you, tiny travellers from the upper sky, racing through warped time, reaching you against all odds. And you? You're not racing, you're not bending time tonight, but you're listening. And sometimes that's even better. You're back on Earth now, not in a lab, not in orbit, not clinging to the rim of a black hole, but right in the middle of your own life. Somewhere familiar, a hallway, a highway, a high school gym. And something is happening. The air is thick and your heart is thudding. Time is stretching. You're in the middle of a crisis, or something close to one. A near-miss car crash, a fall, a sudden confrontation, and your brain does that thing it always does. It flips into high alert, and suddenly, the world slows down. Or does it? Tonight you explore one of the strangest echoes of time dilation. Not cosmic, not mathematical, but deeply personal. This is the sensation of psychological time warp, where seconds feel like minutes, moments stretch into eternity, and your mind plays tricks with the clock even when the physics says nothing changed. Let's rewind. You're watching an athlete about to take the winning shot. Maybe it's the final seconds of a basketball game, or a gymnast suspended mid-air, or a goalie frozen as the ball arcs toward them. To the athlete, everything slows down. They see the motion, calculate the angle, react in what feels like real time, while everyone else watches in regular speed, hearts hammering. And after, they say something like, "It was like time stopped," or "I had forever to think," or "I don't even remember moving." But from the outside, that moment lasted a second, maybe two. Nothing changed in the external world. The clock didn't dilate, but something inside them did. And it's not just athletes, it's you too. You felt it. In those split seconds before impact, in the instant before you said something you couldn't take back, in the quiet, stretching pause after bad news, time somehow feels slower. But here's the kicker. Your brain didn't slow time down. It just remembered it differently. Psychological research has shown that during intense high-stakes moments, your brain switches into hyper-recording mode. It encodes more information per second. You take in sharper visual detail. Your memory traces are denser. So later, when you replay that memory, it feels like it took longer, because there's so much more in it. It's a cognitive trick, a biological illusion, but a powerful one. Historical fact time. In 2007, neuroscientists at Baylor College of Medicine tried to measure whether people could perceive time moving more slowly during a simulated fall. They dropped volunteers safely from a 150-foot tower and had them try to perceive flashing numbers on a special wrist display during the fall. They felt like the fall lasted longer, but they couldn't actually process faster visual data. Conclusion? Time didn't slow down. The memory just expanded. So what you're experiencing in those moments isn't true time dilation, it's subjective expansion. Your internal sense of time stretches, but the world keeps moving on schedule. Still, to you, that moment is longer than a minute, and in your brain, it may be. And here's a delightful twist. We also experience the opposite, psychological time compression. Ever notice how time flies when you're deeply focused? When you're in the zone, engaged in something you love, and the hours just vanish. That's your brain skipping the boring bits. In low stimulus situations, like waiting rooms or lectures on tax code, time drags. But in high focus states, it skips ahead. You don't remember much detail, so the brain compresses the timeline. Poof, 2 hours gone. This is why vacations feel short, why long childhood summers felt eternal, why waiting at the DMV feels like a slow death. Your attention bends time, and it works on a much deeper level than we usually notice. Here's a fringe tidbit. Some studies suggest that people with depression or anxiety experience altered time perception. For those in depressive states, time often feels slowed, not in a helpful, athletic, bullet time way, but in a heavy, unrelenting drag. For those with anxiety, time can feel rushed and chaotic, like there's never enough of it, even when there is. So even our emotional states become a kind of internal time dilation, colouring our hours and days with different rhythms. Historians still argue whether psychological time and physical time are completely separate experiences, or if one influences the other more than we realise. Some neuroscientists suggest that understanding time perception may be one of the keys to unlocking consciousness itself. After all, what is consciousness but a continuous awareness of the passage of time? You're never really aware of a single moment. You're aware of its passing, its transition into the next. And if your brain changes how you perceive that, have you changed time? Well, not for the rest of us, but for you, absolutely. So tonight, as you sink deeper into the softness of your bed, remember, you've already travelled through time today, not at relativistic speed, not by bending gravity, but in your mind, in your perceptions, in those little moments where the world paused or sped up or vanished completely. You're not just living in time, you're bending it, internally, quietly, constantly. Your mind, it turns out, is its own little black hole of experience, distorting seconds, expanding moments, compressing hours into blinks. So the next time the world feels like it's speeding up or slowing down, remember, that's your inner time traveller. No ship, no math, no paradox, and just your brain, doing what it's always done, playing tricks with the clock. And tonight, as you drift further into sleep, notice how the last few minutes felt. Did they stretch or vanish? Maybe a little of both. You're floating again, this time toward the edge of everything, not metaphorically, not emotionally, but physically, cosmically. Because tonight, you arrive at one of the most unsettling, beautiful, and famously misunderstood places in the universe, the event horizon. You remember the black hole, of course, how time bent near it, how gravity stretched seconds into centuries. But now, you're falling closer, no longer observing from a safe distance, no longer orbiting politely. You're headed straight for the line that divides can still get out from nope, you're done. And the weirdness, it hasn't even started yet. So let's set the stage. A black hole isn't a thing, it's a region. A place in space where gravity is so strong that not even light can escape. And the boundary of this region, the point of no return, is called the event horizon. Cross it, and you're not just inside a black hole. You've officially left the part of the universe where anything you do can affect anything else. From the outside, you've vanished. But what does that look like? You're falling now, slowly, steadily, toward the horizon. You've resisted long enough. No more orbiting, no more waiting. Just you and the endless black mouth of space-time. From your point of view inside the falling pod, everything feels normal. No dramatic distortions, no alarms. The physics here is eerily smooth. But to someone watching from a safe distance, say, your overly cautious friend back on the observation ship, you're slowing down. Not physically, but temporally. They watch you descend, your movements stretching into a slow, syrupy ballet. Every signal you send, every photon that escapes your pod gets redshifted. Its wavelength stretched longer and longer until your image fades into total blackness. To them, you never quite cross the event horizon. You just freeze on the edge, like a ghost trapped in an infinite frame of time. This is time dilation turned all the way up. Because remember, the stronger the gravity, the slower time moves, and at the event horizon, gravity is maximum. Time, from an outside point of view, essentially stops. That's not poetic, that's physics. Historical fact check. This isn't a new idea. Carl Schwarzschild first described the mathematical boundary of a black hole back in 1916, shortly after Einstein dropped his general relativity bombshell on the world. Schwarzschild's solution to Einstein's field equations revealed that, mathematically, time dilation becomes infinite at the event horizon. It was one of the first clues that black holes weren't just scary, they were timely. But here's where things get weird, and I mean really weird. From your point of view, falling toward the event horizon, time ticks along as usual, your watch keeps ticking, your thoughts keep coming. If you didn't know any better, you'd have no reason to think you were crossing some boundary. You fall in, clean, quiet, done. But from the outside, you're still falling forever, eternally. Your image frozen on the edge. So which one is true? Welcome to relativity. They're both true, each within its own frame of reference. Time is personal. Your timeline doesn't have to match someone else's. And here, at the edge of a black hole, relativity doesn't just stretch time, It fractures our shared sense of what's real. Fringe tidbit time. Some physicists believe the universe might look like this from a certain point of view. There's a concept called the cosmic event horizon, which suggests that faraway galaxies are already crossing a kind of universal boundary, moving away from us faster than light due to the expansion of space. From our perspective, they're disappearing, and we'll never interact with them again. That means there are already parts of the universe we will never see again, no matter how long we wait. We're surrounded by horizons, not just one. Historians still argue whether the event horizon marks a true edge of physics, or just a mathematical boundary that future theories, quantum gravity maybe, will reinterpret. Hawking radiation, Stephen Hawking's legendary contribution, suggests black holes slowly leak energy and evaporate over eons, complicating the idea of a permanent final boundary. But tonight, you're just falling. Back in your pod, everything seems the same. The cabin lights hum, your breathing echoes, you reach out, touch the control panel. Time, to you, hasn't stopped. But outside, you're frozen, trapped at the edge of time. A shadow image, a memory stretched across 1 billion years. Your voice, stretched to lower and lower frequencies, fades into radio silence. And somewhere, far above, a telescope waits. Your friend stares through the screen, watching your image fade, unsure if you're gone or forever arriving. This is the ultimate one-way trip. A fall into a region where the future has already happened and the past can no longer follow. And here's the real kicker. Once you cross the event horizon, all directions point inward, even time. No matter how you twist or turn, the future leads deeper into the black hole. It's not that you fall in, it's that falling becomes your future. Inside the event horizon, space and time trade places. Time, which once marched calmly forward, now becomes a funnel. You're moving forward in time, and that forward is toward the singularity, a point of infinite density where our physics breaks down entirely. And we don't know what happens there, not yet. Some say it's the end, others say it's a doorway, maybe to another universe, maybe to nothing, maybe to some quantum-braided mystery that won't make sense for another 1,000 years. But from your perspective, you're still inside a moment, a calm one, drifting forward, unaware that time, for others, has long since stopped around you. You're living on the edge of forever, and as you float into darkness, a whisper of thought curls in your mind. Maybe this is what it means to pause, not to stop the clock, but to step beyond it, to cross into a place where time is no longer a question, but an answer. Let's pull you back now, gently, from the brink of that gravitational abyss. You're no longer tumbling through curved space-time or stretching seconds near a singularity. You're sitting somewhere soft again, maybe with a blanket, maybe with tea, and maybe, just maybe, with your mind still buzzing with the whisper of distant physics. So now we get playful. After all that black hole intensity, you've earned a lighter orbit. Tonight we dive into the glowing, over-imagined and occasionally half-correct world of sci-fi tropes. Because if there's one thing humans do with scientific theories, it's wrap them in lasers and give them questionable haircuts. Let's talk aliens, warp drives and time math, and see how much of your favourite fictional science actually holds up under Einstein's moody equations. We start naturally with a starship. It's sleek, it's dramatic, it hums with power in a way that no machine ever should, and it has a drive, a warp drive, that folds space-time so the ship doesn't travel through space, but instead bends space around itself and seems absurd. And yet, in 1994, a physicist named Miguel Alcubierre proposed a theoretical model for this very thing. He called it the Alcubierre drive, and it suggested that if you could contract space in front of a spacecraft and expand it behind, the craft could ride a warp bubble faster than light without technically breaking the speed limit. Inside the bubble, the ship doesn't move, but space-time does. Yes, this was published in a real physics journal. Yes, it's based on Einstein's equations. No, it's not science fiction. But here's the problem. You'd need exotic matter with negative energy density. A kind of matter that, if it exists, might violate a few things we consider sacred, like conservation laws. Oh, and the energy required might be more than the mass of the observable universe. Minor hiccup. Still, warp drive sits in that weird zone of science where the math says, sure, I guess, and the reality says, not unless you're dreaming. Which, lucky for you, you are. Now let's add aliens. You've probably heard this one. If an alien civilization figured out faster than light travel, they could zip across the galaxy in no time. But here's where time dilation throws a wrench in the story. If you travel at near light speed to another star, time slows down for you. You could make the trip in a few years of your own time. But back on Earth, decades or centuries would pass. So an alien who visits us by high-speed ship might experience the trip as short, but when they arrive, they're in a completely different version of our world. Languages have changed, cultures have shifted, Starbucks might finally be gone, and the reverse is true. If we go visit them, we leave behind everyone we knew. The price of high-speed travel isn't fuel, it's time. And that's why some scientists suspect that advanced civilizations, if they exist, don't bother with star hopping. Not because they can't, but because the time math is a nightmare. Quirky sci-fi detail for your consideration. In Interstellar, the characters experience extreme time dilation on a planet near a black hole. 1 hour on the surface equals 7 years off-planet. This isn't a plot gimmick. It's scientifically accurate, according to Kip Thorne, who helped design the film's physics. So yes, Hollywood got one right. Mark the date. Historians still argue whether all these fictional faster-than-light methods, warp drives, wormholes, hyperspace, are creative speculation or just lazy storytelling. But here's the key difference. Real time dilation doesn't require cheating physics. It's already baked in. Want to travel to the future? No need for a glowing core or a wormhole powered by friendship. Just build a ship that goes really fast, ride it for a year, and come back to find Earth has aged without you. That's the hard science version of time travel, and it's far more dramatic than most fiction gives it credit for. Now let's get weirder. There's a famous hypothetical called the tachyonic anti-telephone. The idea is, if faster-than-light particles, tachyons, exist, you could use them to send messages backward in time, not just to other places, to other moments, which breaks causality in so many ways it practically folds the plot of your life into a pretzel. Say you receive a tachyon message saying, "Don't go outside," so you stay in. But then, why was the message sent in the first place? This is the grandfather paradox wearing digital sunglasses. Time math, when bent too far, starts to undo itself. And yet, we keep writing stories. Because bending time isn't just physics, it's hope. Hope that we could fix something, revisit something, skip the hard parts, say goodbye, or hello, or just understand the future before we have to live in it. That's why sci-fi loves time travel. It isn't about science, it's about control, about bending the one thing none of us can escape. But you, lying here now, know the real truth. You don't need warp drives to experience time differently. You do it every day. You stretch it when you fall in love. You collapse it when you lose someone. You skip forward in dreams and drag your heels in grief. You've lived entire lifetimes in minutes and waited forever in a line at the DMV. Because time, even when played with in fiction, is never just about seconds. It's about meaning, about weight, about what you do with the hours you have. So tonight, as you imagine your own warp bubble, your own ship slipping through space and story, remember, time doesn't need to be broken to be beautiful. It's already doing its own slow, strange dance. And you're dancing with it. No light speed required, you've come so far. Through speed and gravity, fiction and fact, muons and migraines. You followed time as it stretched, slowed, slipped, and sometimes vanished altogether. And now you arrive at the question that quietly haunts all the others. Is the future already there? Let's walk gently into this one. You're used to thinking of time as something flowing, like a river, carrying you from the past to the present, and onward to a future that doesn't yet exist. It feels obvious, intuitive. The past happened, the present is happening. The future, not yet. But physics? Physics doesn't see it that way. In fact, some of the most respected theories in physics, relativity included, suggest that past, present and future all coexist. Not like stepping stones you hop between, but like a block, a space-time loaf where every moment is just another slice. You don't move through time, you are time. This is the block universe model. Also called eternalism, it's the idea that time is a dimension, just like space, and that every event, birthdays, breakfast, heartbreaks, black holes, already exists in the four-dimensional structure of the universe. From that perspective, the future isn't waiting. It's already written, just not revealed. If you're blinking right now, don't worry. Most people do, and let's break it down. Imagine a loaf of bread. Not the sliced kind. The whole thing. Thick, Soft, still warm, that's space-time. Each tiny layer in the loaf represents a moment, not a second, not a tick, a now. And they all exist, baked in, unmoving. You're a conscious being moving along that loaf. Your perception, your attention, slides forward through the layers. But the loaf itself, it's already whole, already there. You don't create the future by moving into it, you just uncover the part of the loaf you're currently in. And here's the truly bizarre part. From a physics standpoint, there is no single now. What's happening now for you might be not yet for someone moving differently. Einstein proved this with his relativity of simultaneity. The order of events depends on who's observing. One person might see event A happen before event B. Another, moving at a different speed, might see event B first, and neither is wrong. Historians still argue whether Einstein personally embraced the block universe model, but he did once write to the widow of a friend, "For us physicists, the distinction between past, present and future is only a stubbornly persistent illusion." He wasn't being poetic, he was being precise. So what does this mean for you? If the block universe is real, then every moment of your life already exists. Your first birthday, your last goodbye, that perfect summer afternoon, that one time you laughed so hard you forgot what you were laughing about. They're all still there, still happening, still part of the loaf, yet you just can't access them all at once. But the weird part is, maybe someone could. From outside the block, from a higher dimensional viewpoint, the way you can look at a whole road from a drone's perspective, even though the driver below can only see what's ahead. Maybe consciousness itself is just a spotlight moving along a fixed film reel, illuminating each frame as now. And maybe, just maybe, there are beings, real or imagined, that see all the frames at once, all the nows. And if you're wondering what free will means in this picture, well, that's the fun and terrifying part. If every moment already exists, do you actually have choices? Or are you just playing out a script that was always going to happen? Some physicists and philosophers say yes, you're following a path. Every decision, every pause, every detour, already written. Others say that even if the future exists, you're still making choices, that your freedom comes from the fact that you don't know what's next. Just like flipping through a book you haven't read, each page exists, but your path through it is still yours. And here's a strange little fringe tidbit. Some theories of quantum mechanics suggest that the future might affect the past, not just through cause and effect, but through something called retrocausality, where particles seem to know what's coming and change their behavior accordingly. Is that proof the future exists, or just more quantum shenanigans? No one knows. But the idea that time might be more landscape than arrow, that everything you've ever done and will do already exists, has quietly reshaped how we think about identity, memory and mortality. Because if the future is already there, then you're not moving toward it. You're just discovering it. Like a sculpture hidden in marble, like a photo developing in reverse, like a dream you're already dreaming 1 second at a time. So tonight, as you drift beneath the covers, think about all your moments, the ones that feel gone and the ones you haven't met yet. They're not lost, they're not waiting. They are there somewhere in the block, still bright, still breathing, still part of you. And the next moment, it's already ready. You just haven't stepped into it yet. And now, finally, you pull back. Not from a black hole, not from a paradox, but from the entire cosmos. As if you're rising high above the universe itself, watching everything unfold. Stars exploding, galaxies spinning, clocks ticking, people rushing around beneath clouds that don't know your name. This last step isn't about one experiment or one theory. It's about the big picture. The question that echoes through every ticking watch, every decaying muon, every GPS satellite, every whispered dream of warp speed. Does the universe care how fast your clock ticks? Let's sit with that. All the time dilation you've explored, due to speed, gravity, motion, memory, mood, it's personal, local, individual. Time warps for you depending on your path through space-time, your gravity, your velocity. The laws of relativity never change, but the experience of time always does. So zooming out, way out, what about the universe? The whole thing? Well, the universe isn't ticking along on some giant cosmic wall clock. There's no absolute tempo, no shared playlist of seconds. Each object, planet, particle, person has its own metronome, its own private beat. Relativity ensures that. But does anything hold it all together? Actually, yes. It's called proper time. the time experienced by a particular object along its path through space-time. Every astronaut, every atom, every apple has its own proper time, and from that perspective, the universe is self-consistent. Everything obeys the same rules, even if their clocks don't match. The equations of general relativity care about relationships, not about global synchrony. Time isn't something that drips down from a cosmic ceiling. It's something that emerges from within the system. Like temperature, like pressure. You don't measure universal time, you measure relative intervals between events, between here and there, before and after, which means from the universe's point of view, if it has one, time isn't absolute, and it's certainly not special. It's not some master rhythm everything marches to, it's just a consequence, a product of geometry, of mass and energy and curvature, and yet, time still feels special to you. You wake up, you age, you remember, you plan, you mark anniversaries and set alarms and feel it pass in your bones. Even if time is emergent, even if it's relative, even if the cosmos doesn't care, it matters to you, and that makes all the difference. Historical anchor. In 1927, Belgian physicist and priest Georges Lemaitre proposed that the universe had a beginning, a primeval atom that exploded outward in what we now call the Big Bang. Since then, time has been expanding with the universe. Every second that passes is another notch in cosmic history. Stars burn through their fuel, galaxies drift apart. Even now, time and space are expanding together. But again, here's the kicker, that expansion doesn't happen at the same rate for everyone. A galaxy in a massive cluster might age differently than a lonely one in a cosmic void. Their clocks don't tick the same. They never have. And still, things work, stars still shine, atoms still bond, life still happens. So no, the universe doesn't care how fast your clock ticks, but it also doesn't stop you from making meaning out of it. Here's your fringe thought for the finale. Some researchers in cosmology and quantum gravity have suggested that time itself might dissolve at the deepest level of the universe, that when you get small enough, fast enough, energetic enough, time loses all meaning, that maybe in the earliest moments after the Big Bang, time wasn't even a thing yet, just potential, just symmetry. So maybe time isn't part of the foundation of reality, maybe it's part of the scaffolding we use to make sense of it. But does that make it any less real to you? Not at all. Time may be an illusion, a convenience, a local habit of matter and motion, but it's also where you live. It's the space between moments, between people, between memories. It's the distance between what you were and what you're becoming. And in that sense, the universe doesn't need to care, because you do, and that's enough. So as you rest now, eyes heavy, mind stretched across centuries of thought and miles of space-time, you carry one truth with you. You are part of this strange, bending, unshared ticking. Your clock ticks uniquely. Your path through time is yours alone, and even if the universe is indifferent, time still moves because you do, and tomorrow, it'll be waiting, in its own way, in its own time. So here you are. Not at the end of time, but at a quiet little moment along its endless winding thread. You've travelled far tonight. Not across galaxies, not into the past or future, but into the folds of what time really is. You've watched clocks slow and memories stretch, seen light bend and munes linger, stood on the edge of black holes and peered into futures that might already be there. But now, there's no need to understand, no need to measure. Just breathe. Let each breath be a tick, not of a clock, but of your body's own rhythm. Let the muscles soften, let the tension go. Time will keep ticking whether you notice it or not. There's nothing to chase, nothing to hold. The seconds don't need you to count them. They'll be here, quietly arriving one after the next, whether you're watching or dreaming. So let yourself drift now, through sleep, through stillness, through a slower kind of time. The kind that doesn't hurry, the kind that doesn't ask, the kind that just is. Tomorrow will come, as it always does. The sun will rise as it always has, and you'll open your eyes in the only moment that ever truly matters. Now. So close them now. Let the world fade, and let the quiet carry you forward. You've bent the clock enough for one night. Sleep well, time traveller.